So here's the problem. During emergencies, people need rapid access to refrigerated supplies and medicine. Many vaccines must be stored at temperatures under 10 degrees Celsius or 50 degrees Fahrenheit. This requires refrigeration in order to be consistent. COVID-19 poses a new issue, however. We must deliver medical supplies and vaccines to quarantined areas. The question is, how can we distribute refrigerated goods quickly while minimizing the number of humans involved? So current methods involve sending medical professionals to a location with personal protective equipment. This includes gloves, face masks, goggles and hoods, and more. And all of these things must be either cheap and disposable or sanitizable for reuse. This equipment is in short supply and not exactly foolproof. More people are being put at risk just to transport this medicine to facilities. But what about drones? Drones can be an asset to fighting COVID-19. They cut down on human contact. China has recently been experimenting with drones in order to spray disinfectants, transport test samples, and deliver consumer goods to people in quarantine like any other delivery drone. But what if you wanted to transport something that needed to be refrigerated during a trip and monitored the whole way, like a vaccine or an EpiPen without needing the insulating case, an insulin, or anything else? This problem is what led to our project idea. So our solution is a tiny refrigerator that can easily be lifted by a drone. In order to do this, it would need to be able to carry up to 1 kilogram of cargo, maintain a temperature of less than 10 degrees Celsius, and be able to operate off of either the drone's battery during flight or through a wall outlet after the trip. We also decided to build a drone to test this with. The drone would have an automatic navigation software, and it would be able to use computer vision for takeoff and landing. This is our system where we have a ground control station, the delivery drone with its computer vision system, as well as the micro fridge, which is able to be detached from the drone at any time. So let's get into the first part.
Hello, I'm Eric, and I'm going to be discussing the microfridge section of the delivery drone. The microfridge is essentially needed to keep whatever supplies that are being carried on the drone cold, particularly medical supplies. A conventional refrigerator is just far too big and far too heavy to be transported using a drone. So a thermoelectric cooler was used. The thermoelectric cooler is also known as a Peltier module and relies solely on voltage and current to run. They're a lot lighter, but they're a lot less efficient. The insulated box section of the entire microfridge was designed by Peter using styrofoam sheets. These sheets were essentially just cut in half and hot glued together to make a solid sealed box. The power delivery circuits were designed by Eric using LTSpice. LTSpice is a great simulating software, and we were able to develop a buck converter that can convert the 14.8 volts from the battery to 8.2 volts as needed by the Peltier module. The buck converter is controlled using a 555 timer to turn on and off the PNP transistor used. The battery, when implemented, is connected to the box using an XT60 connector from the battery to the power delivery system on the box. As you can see, when run at full power, the Peltier module gets very cold on one side and even has frosting developing. As such, this is not desirable. So to resolve this issue, a Peltier control circuit was also needed. A control circuit was chosen as an SCR switch that can be turned on and off using two MOSFETs, S1 and S2, where S1 turns it on and S2 turns it off. And this is controlled using an Arduino Uno, hooked up with LM35 sensors inside the box. And if it reaches above a certain temperature, it turns on, and if it reaches below, it turns off. Now to move this heat transfer around both inside the box as well as the heat from the hot side of the Peltier module, fans were needed. Fans that were chosen are 12-volt DC fans that run most optimally at 75% power, so at around 9 volts. To power this, since these don't need to be as regulated as the module, they were used using a simple Zener diode reference circuit as shown below.
Hello, my name is Alex Murray, and on this project I was responsible for the drone. When we were designing the drone, we envisioned an aircraft which would be able to carry a 2-kilogram payload, deliver that payload with a radius of at least 10 miles, and provide enough power both for the engines and for the refrigerator. Early on in the design process, we designed that a quadcopter built out of 6061 T6 aluminum using an H-frame would be the best design decision to meet this challenge. Autodesk Inventor was used to design multiple different versions of the airframe itself and test this airframe under the maximum predicted operating stresses to verify it would be able to withstand them. Once the chassis was designed, the next task was to determine the appropriate power electronics, engines, and propellers to use. In order to make this decision, manufacturer data and manufacturer thrust data was used. Eventually, we decided to use the APC 10x4.5 propeller with the Cobra motor. Once the engines, propellers, and chassis were designed, MATLAB was used to predict the performance of the drone based on the laws of physics and on the published motor and propeller data. The next step was to actually program the flight control avionics. On board the drone, a Kalman filter is used to fuse data from an accelerometer, gyroscope, and magnetometer in order to estimate the drone's orientation in 3D space. Then, a PID controller, proportional integral derivative, is used to perform navigation tasks and apply throttles to the motors as appropriate. Finally, the software had to manage telemetry and communications with the ground station. Here we can see a Simulink diagram of the onboard PID controller. The architecture of the PID controller we used was a layered PID controller with the inner layer controlling angular velocity about the 3 axes, the second layer controlling altitude and attitude, and the final layer controlling position in 3D space. Here we can see a block diagram of the onboard avionics and the ground station software. On the ground station, a workstation with a flight controller, such as a joystick, or in our case, a gamepad, is used to send commands to an Arduino microcontroller over UART. The microcontroller then relays these commands via SPI to our radio transceiver, which uses a proprietary protocol called Enhanced Shock Burst to send this data to the drone. Once at the drone, the Arduino Mega microcontroller onboard the drone receives this data and, together with the onboard PID controller and Kalman filter, determines the appropriate signals to send to the motors. In order to actually build the drone, some tools were necessary. A machine shop containing a milling machine, drill press, and bandsaw were used to fabricate the elements of the drone chassis as well as the drone brackets. The Rutgers ECE Capstone Lab was used to install motors, motor speed controllers, battery gauge, and propellers. In addition, the soldering stations in the lab were used to assemble the wiring harness. Once the avionics power electronics were installed and the chassis was completely assembled, it was time to do some testing. It was necessary to test the drone in order to calibrate the autopilot and confirm that the Q and R values for the Kalman filter were correct. In order to do this, a rudimentary single-axis gimbal was built and used quite thoroughly in order to calibrate the autopilot on both the roll and pitch axis. In addition, the proper functioning of the radio telemetry system was verified in order to ensure safe operation. Unfortunately, disaster struck, and we were not able to fly the drone in time for the expo. An electrostatic discharge event, which occurred about a week before Capstone Expo, destroyed the IMU, which contains the accelerometers and gyroscopes. This rendered the drone unsafe to fly. Due to shipping delays associated with COVID-19, a replacement IMU unit could not be procured in time. Despite this, we were able to cause the drone to hover with stability on the testing rig. An important lesson was learned from this failure. Always have backups of critical parts.
For the automatic landing, we plan to use the OpenCV computer vision library to handle landing on a checkerboard pad, like so. For the object detection, we were planning on implementing a pedestrian detection algorithm to give the drone an unobstructed path from its start point to its destination, thus avoiding any collisions with any people and hurting anyone or damaging the drone.
The ground control station provides information about the drone to the user. Information such as the battery levels, the cooling temperature, how fast the drone is traveling, and the drone's current location. It also allows the user to control the drone either autonomously or manually. You can also add the routes for where you want the drone to go and things like that.
The format and communication. We wanted to format it similarly to TCP, used for internet data transfer, with a send message and a acknowledgement message. The ground station would send a message requesting data from the drone, and the drone would acknowledge that specific request number with the data that it had requested from it.
The closing of campus due to COVID-19 meant that we could not fully implement our project. We were planning on integrating the computer vision and remote flight control software into our drone. We were planning on testing the Peltier cooler with the battery, and housing the Peltier cooler into the insulated box and recording data for the cooler's efficiency. But considering the limitations, we achieved a lot. We have a nearly flight-ready delivery drone, despite some complications. We have a Peltier cooler proven to work with our power electronics using a plug-in power supply. We have early computer vision and radio connections. And we have basic flight control and communications software. We believe that with further work, our system could rapidly deliver refrigerated medical and non-medical supplies to people in difficult-to-reach locations.